Welcome to my online course in linear algebra for undergraduate mathematics. Linear algebra is a branch of mathematics that deals with the study of vectors, vector space, and linear map, also known as linear transformation. It deals with the study of linear equations, linear functions, and their representation through matrix and determinant. In this course, we will study vector space, linear combinations, linear independence, linear dependence, linear span, basis, dimensions, linear transformations, kernel, matrix representations of the linear transformations, eigenvalue and eigenvectors. Finally, the course ends with inner product space, definitions of the inner product space, orthogonality, orthonormal sets, orthonormal basis. As I already stated, this is an online course. My sincere suggestion to the student is to attend all their classes in their college. Give regular attendance to the regular attendance in your class. This course will help you whenever you forgot some concept that you have taught in your class, and whenever due to unavoidable circumstances, unavoidable problem, you will unable to attend your class, but the personal confrontations of teacher and student are required. So my sincere suggestion is to attend all your classes regularly, as in the word of Alan Carter, given the will and the desire, one can obtain knowledge from book, TV, skin, the magnetic trap, but the wisdom, understanding, and tolerance, the essential aim of the liberal learning, are attained through personal confrontations of the teacher and student. The textbook for study of linear algebra is you can follow any standard textbook. We generally recommended the textbook provided recommended by the affiliated university. Our college is affiliated to Assam University. Textbook recommended by Assam University in the syllabus is S. Kumarisian Linear Algebra, a Geometric Approach. Prerequisite required for this course is classes 12 standard mathematics, especially the chapter matrices and determinant vectors. Next is classical algebra or higher algebra, especially the rank. You must know how to determine the rank of a matrices by echelon and normal form, and the solution of the system of linear equations, both homogeneous and non-homogeneous. Then you need the basic definitions and result of group theory and ring theory. Next is vector space. Vector space originated in the study of vector in geometry and mechanics. A vector in maths defined as a directed line segment. Defined as a directed line segment. The initial and the terminal point of the terminal point with respect to a fixed coordinate system is known as is regarded as ordered pair. So vector addition is defined as this. These are the here. This is initial and terminal point of the first vector sum with added with the initial and terminal point of the second vector. Here vector addition is defined element wise, that is first element add with the first element of the second vector, second element add with the second element of the second vector. Then scalar multiplication. Scalar, if alpha is any scalar, then scalar multiplications of alpha with uh, initial and terminal point will increase or decrease the length of the vector by magnitude alpha. The next is geometrical representation. Geometrical representation interpretations of additions and scalar multiplications of two vector. Here we have two vector. One represented by blue color, another represented by red color. To obtain the vector addition, we have completed the side of parallelogram. Then this diagonal will give the addition of two vector. That is the lowest. You move starting from the initial point of the red color vector. Then this vector parallel to this will represent the p vector. Then if we move in this way, starting from left side in anti-clockwise direction, then this resultant, that is diagonal, will give the addition of the vector. Both this will be the direction and this is the magnitude b plus w. Next, if we scalar multiply the vector w with an scalar 2, then its magnitude will be increases and the resultant vector additions will be b plus 2w. It will be get in the same way as we get vector addition in the first figure. In the study of vector space, we will not restrict ourselves to the real line R only, but we will take any field F. Now this is definition of vector space. We consider F to be a field and B plus be an additive abelian group. Then B is said to be vector space over the field F if there exists a scalar multiplications. Alpha belongs to F, B belongs to F, alpha B belongs to B, not F. Which satisfies the following four conditions. Number one, alpha is a field element multiplied with the addition of two vector elements u and p equal to alpha u, that is field element multiplied with the vector element plus field element multiplied with the vector element. Number two, alpha plus beta with u is equal to alpha u plus beta u. Finally, this is the associativity between the element of the field and the vector. Alpha beta u is equal to alpha beta u. If 1 is the unity element of F, then 1 into u is equal to u. This here multiplication is not our usual multiplication. This denotes the binary operations. This is a notation for binary operation. The element of P are called vector and the element of F are called scalar. If P is a vector space over F under the same additions and vector additions and scalar multiplications, then we say VF is a vector space. Vector space are also known as linear spaces. This definition usually we give to the honors level mathematics student. But in case of engineering background, we slightly change the definitions as they are not well aware about the technical terms such as field, group, ring, and abelian group. In that case, you should take F to be the set of all scalars and B be the set of all vectors. B be the set of all vectors. Scalar multiplication, that is also known as external multiplication, is defined in the same way. Alpha in the set of scalars and B in the set of vector. Alpha B in the set of vectors. Then we say that 12 more conditions in addition to these 4 is satisfied by a set to be vector space over the field F. These conditions are: number 1, B is closed under vector addition, that is u p belongs to P implies u plus P belongs to P. Element of P is associative. All of us know what is associativity because we all study this from class 3-4 onwards. Associativity. Here it is same as our field is a general field have. So we consider plus as only the notation to denote the binary operation. So if ABC are any three element of P, A plus B, A bracket B plus C is equal to A plus b within bracket a plus b plus c. So this is the property of associativity. Next, V must have additive identity. What is additive identity? For any element A in V, you must have an element 0 belongs to V such that A plus 0 is equal to A, and it is equal to 0 plus A. In that case, 0 is act as an additive identity of P. Next is additive inverse. For any element A in B, we must have some element we must have some element B in B such that A plus B is equal to the 0 of B. And A plus B is equal to 0. Again, it is equal to B plus A. In that case, we said B equal to minus A is the additive inverse of A in B. Again, plus is associative in half. We have already defined what is associativity in half. Plus is commutativity in half. That is, take any two element of half. Alpha, beta, any two element of half. If alpha plus beta is equal to beta plus alpha, then it is called commutative. Next is additive 0. Additive 0 for any element, additive 0 in half. That is, alpha is any element in half, then there exists an element 0 belongs to half such that alpha plus 0 is always alpha, which is equal to 0 plus alpha. Then it is done. This 0 is called additive inverse or additive 0 of f under plus. Next is additive identity. For any alpha belongs to half, there exists another beta belongs to half such that alpha plus beta is equal to 0 is equal to beta plus alpha. Then this alpha is a additive inverse of beta. Okay. Next, f is associative as well as commutative with respect to multiplications. That is, you also replace all plus symbol by dot in case of multiplications. F is unity element. That is, for any element A in F, there exists always one element 1 in F such that 1 into A is equal to A. Okay. Next, in case of field, you have every non-zero element of F possesses multiplicative inverse. What is multiplicative inverse? If A belongs to F, there exists another element B belongs to F such that A into B is equal to identity, is equal to B into A. Then we say A is the inverse of B or B is the inverse of A. In addition to this, if it follow the following four conditions, then we say vector space. So in case of engineering, we give the definition slightly different from the definition of vector space we give to honors student of mathematics. As honors students are familiar with technical terms like group, ring theory, abelian group, properties of group, but these engineering students, BTech students, are not familiar with these technical terms. So we used to give them the 12 conditions in addition to these 4 conditions. Next is the properties of vector space. If VF is a vector space over the field F, then alpha is any element in half UB or any element in V, then we have alpha 0 vector equal to 0 vector. That means scalar multiplied with a 0 vector. 0 is from B, alpha is from F, then resultant will be the 0 vector of B. Okay. Then if 0 come from F and B come from B, then resultant will be the 0 vector of B. Okay. Next is alpha is a scalar and negative of a vector come from this B. This is equal to minus of scalar into the vector. this is equal to minus of scalar into the factor. Fourth property, minus of scalar and minus of factor is equal to product of the scalar and the vector. Fifth, alpha of alpha multiplied with the subtractions of two vector is equal to alpha u minus alpha b. If alpha b is equal to 0, that is product of scalar and the vector is equal to 0, then either alpha is equal to 0 or b is equal to 0. Now come to the proof. Here we have taken left hand side of the left hand side of 1, that is alpha 0. Alpha 0 can be written as alpha 0 plus 0 vector plus 0 vector. Here it is, alpha is a scalar and 0 vector is a 0 of v. So that can be written as alpha 0 plus 0, because 0 is an additive identity. 0 has its own inverse, so 0 plus 0 is equal to 0. So I am writing this alpha 0 plus 0. By left distributive property, I can write this alpha 0 vector plus alpha 0 vector. In the left hand side, 0 plus 0 vector plus 0 vector is 0 vector. That will give you alpha 0 vector. In the right hand side, by distributive property, we get alpha 0 plus alpha 0. Then alpha 0 become the element of v. This is an element of v. Now with that I am adding the 0 vector. That will not create any change to this vector. So this is alpha 0 plus 0, which is equal to alpha 0 vector into plus alpha 0 vector. By left cancellation law, we will get alpha 0 vector equal to 0 vector. What is left cancellation law? Yeah. Take any three element A, B, C of V such that AB is equal to AC. If A is not equal to 0, then we can cancel out this AA from the left hand side of the statement, AB equal to BC. This implies BC. So this is the left cancellation law. Now take the second one, 0V is equal to 0 vector. I am taking the left hand side 0V, since by using the definitions of additive identity in F, 0 can be written as 0 plus 0, 0 plus 0, V is equal to 0V plus 0V. Since 0 is the additive identity, it has its own inverse, so 0 plus 0 is equal to 0. This implies 0v is equal to 0v plus 0v. Now this 0v, 0 is an element of field and v is an element of vector, so this resultant 0v is an element of vector. So this is equal to, here if I add a null vector, then this equation remain unchanged. This equation can equivalently written as this equation. Okay, now applying the left cancellation again, I will get 0v equal to 0 vector. Then for the third property, we will take alpha u plus m minus u, that is element with its additive inverse. Then by left distributive, I will get alpha u plus alpha minus u. In the left hand side, element with its additive inverse is always a 0 vector. So alpha, this portion will be my 0 vector. So I am writing here this is 0 vector, and this alpha u plus alpha into minus u. Okay, this is not into here, this is not multiplication, this is the binary operation, stand for scalar multiplication. Whatever the binary operations provided in the space, that binary operation. Okay, do not get confused between our usual multiplications and this binary operation, scalar multiplication. So this is 0 This vector will be the alpha is a scalar and this is a 0 vector, that will be a 0 vector, and this is alpha u plus alpha minus u. What it mean? This is an element plus, if I take this a and this as b, a plus b is equal to 0 vector, that means one is the inverse of the other. Here you can take this minus of this and this minus of this, as my requirement is this minus of this, so I'm taking this, and this statement will be proved. Again, to prove one side of the statement, I'm taking minus alpha plus alpha u, that can be equal to, by left distributive, this is from right distributive, minus alpha u plus alpha u, this implies minus alpha plus alpha is equal to 0, 0 of scalar 0, not vector 0. You must know, as a measure level student, you must know where the element belongs, whether it belongs to the scalar field f or whether it belongs to the additive abelian group P. Okay, so here minus alpha plus alpha, that is element with it additive inverse, it is 0, as alpha belongs to the set of field. So this is a scalar 0 multiplied with u, and this is minus alpha u plus alpha u. That means this is by second property. This is 0 vectors. 0 vector equal to this one. 0 vector is equal to this one. That is, if I take this as a, this as b, where a plus b is equal to 0 vector. That is, one is additive inverse of other. So I can write b is equal to a is equal to minus b. That is, minus alpha u is equal to minus alpha u. Okay. Next, minus alpha minus u. So if I consider this as a and this as minus b, by using third property, this property, this can be written as alpha within bracket minus u. Again, if I apply this property here, this is b and this is a and this is minus b. Again, by this right hand side, by this property, I'm getting this one. I'm getting this one, minus minus of alpha u. Minus minus become plus, that is alpha u. Finally, I will get the property minus alpha minus u is alpha u. Okay. Now fifth property is alpha u minus p is equal to alpha. You can write u plus minus of p, that can be written in the next step as alpha u plus alpha minus p. By which property? It is by left distributive property. Again, using the third property, I can write this in place of this. Using this property, I am writing this minus alpha u. Some of the students write it directly by the knowledge of writing ABC real number in case of integers and natural number, but you must know the differences, how the things are coming from the space. Okay, these proofs are looking very trivial, but you must know the concept, idea behind each step. Okay. Sixth property, let alpha be equal to 0. Let alpha be equal to 0 vector, then either alpha is equal to 0 or p equal to 0. We are going to prove this one. First of all, suppose alpha is not equal to 0, then alpha inverse exists. Now alpha be equal to 0 vector implies this. That means we are pre-multiplying this equation by alpha inverse. I will get this one. Alpha inverse, alpha inverse 0 vector. Now by the property of vector space between the associativity property of the vector space between the element of field and vector, I can write this one. Alpha inverse alpha b equal to 0 vector. Alpha inverse alpha is the additive identity of the field, that is 1 b equal to 0. So 1 into p is equal to p by the definitions of the properties of f Properties of vector space, sorry, not the field. Because here one is the element of the vector space, other is the element of the field. So it is by the definitions of the vector space be equal to 0. Next, let v be not equal to 0. We will going to show that alpha is equal to 0. We are going to prove this by contradiction method. That is, first of all, we will suppose that alpha is not equal to 0, as alpha belongs to f. So f is field. Alpha inverse exists. So again pre-multiplying this equation alpha 0 by alpha inverse, I will get this one b equal to 0, which is a contradiction, as we have not as we have considered in the beginning b is not equal to 0. Therefore, this contradiction arises because we have considered alpha is equal to 0. Therefore, alpha must not equal to 0. This contradiction arises because we have considered this alpha not equal to 0. We are going to show this alpha equal to 0. So I am getting alpha equal to 0. Next is an example on vector space. Consider R2 over the field R. Vector addition is defined in this way and vector scalar multiplication is defined in this way. You have to check whether under this vector addition and scalar multiplications R2R is a vector space. For that, take alpha equal to 1 and beta equal to -2. Consider a ordered pair. 3, 4 belongs to R2. Then check out what is the value of alpha plus beta x. Beta x, here exists the pair 3, 4. Here alpha is 1, beta is -2. So alpha plus beta will be 1 plus -2. That will be your -1 into 3, 4. That using these definitions of scalar multiplications, this is -1, absolute value of -1, 3, comma, absolute value of -1, 4. That will be your 3, 4. And again, take alpha x plus beta y. That will be your 1 into 3, comma 4 plus -2, comma -2 into 3, comma 4. Using this definition of scalar multiplications, I will get absolute value of 1 into 3, comma absolute value of 1 into 4 plus absolute value of -2 into 3, comma absolute value of -2 into 4. That will give you 3, 4 plus ordered pair 6, 8. If you add this to ordered pair by using these definitions of the factor additions, then you will get 9, 12, which is not equal to 3, 4. So this condition is not satisfied, and therefore we conclude that R2 is not a vector space. Okay, under this scalar multiplications, R2 is not a vector space. This one is for your practice. You should solve it at your own. In case of any problem, any difficulty, you can ask me. I will solve it for you. But this question is exactly same as the previous question. I hope you can solve this one. But in case you get stuck, you get some problem, you can ask me. I will solve it for you. Next is some more examples of vector space. 0 and pure trivial vector space. They are automatically vector space over itself. Okay. Next is every field is a vector space over its subfield. This question I have no option to prove it by taking F as a field and K as a subfield. Actually, such kind of question never asked it in never asked in B and BTech syllabus. So very rarely asked such kind of questions. So I am proving this using little field and subfield. But in case this question is asked to engineering gadget, they can solve it by using the six instead of showing that it is closed under vector addition and scalar multiplications. In addition to that, it will satisfy the 4 conditions to be a vector space. You should show 12 more additional points that is required for vector space. I am leaving it to you as a assignment, home assignment. You should solve this in your home. In case of any problem, any difficulty, you can ask me. I will help you to solve this one. Okay. Now I'm proceeding with the proof for honors students. Let F be a field and KB is a field. We have to show Fk is a vector space. If we consider addition in F, then by definition of field, F plus is an additive abelian group. F is a field if F a non-empty ring is a field if F plus is an additive abelian group and F dot is a multiplicative abelian group. So here if I consider addition in F, then F plus is the additive abelian group. Okay. Next, I consider alpha in K, where K is a subfield of F and P is in the field F. As K is a subfield of F, this alpha belongs to K and K is a subfield of F, alpha finally belongs to F. Then since element of F are closed under multiplication, so alpha B belongs to F. So F is closed under scalar multiplications. F plus is my additive abelian group. F is closed under scalar multiplications. Now I am done. If I show, if anyhow I will show the F satisfies the following remaining four conditions of the vector space. Take the first conditions, alpha u plus p, which is equal by left distributive law of F. I will get alpha u plus alpha p. Already I have shown that if alpha beta belongs to K, then it trivially belongs to F, and UV belongs to F, and element of F follow the left distributive law. So alpha u plus p is equal to alpha u plus alpha b. Next, alpha plus beta u is equal to alpha u plus beta u, which follows from the right distributive law in F. Finally, alpha beta u is equal to alpha beta u, which follows from the associativity of multiplications in F. If one is the unity element of K, then one is also the unity element of F. Then for any element in F, I will get 1 u is equal to u. Thus, Fk is a vector space. However, the converse is not true. For example, consider the field of complex number and the field of R under usual addition and multiplications. Okay, under usual additions and multiplications, that is plus and multiplication. C is a vector space over R. But converse is not true. R is not a vector space over C, as R is not closed under scalar multiplication. For example, take 3 belongs to R and 5 plus 2i belongs to C. Then this is not 2, this is 3. If you want to keep it 2, here change it to 2. Otherwise, change it to 3. Okay. Then here I am taking this 3. 3 into 5 plus 2i does not belongs to her, as this is a complex number does not belongs to her. So converse of the above is not true. That is, a field is a vector space over its subfield, but subfield is not a vector space over its field. Okay. Next example is the set of all m by n matrices with entries from field is a vector space. Come to prove, if M is the collections of all m by n matrices, its elements belongs to field. Here, matrices are rectangular arrow of element arranged in M row and n column. Okay, if A is Aij, B Bij, and C Cij be any three element of M, that is, there are any three matrices of m by n type, then we define A plus B equal to Aij plus Bij. Clearly, A plus B is an M by N matrix, said I have already said to you. Also, Aij, Bij belongs to F for all Ij. So F is closed under addition, so their sum belongs to F. Aij plus Bij belongs to F. Therefore, A plus B is equal to Aij, Bij belongs to M. That is, A plus B is a M by N matrices. Okay, matrices of this collection M. Therefore, M is closed under addition. Here, I have shown the associativity and commutativity manually, but you can, if you know the properties of matrices, then you can directly write that addition of matrix and addition of matrix is associative as well as commutative. Okay, no need to go for this calculation or no need to go to show these steps. But you have to check it out, the additive identity. You should take, let 0 be the null matrices of order. This is not n, this is m by n. Okay, this is m by n. This is typo, writing mistake, not writing mistake, typing mistake. With all its entries 0, then 0 belongs to the set of all m by n matrices. Now for any matrix A of the collection, from the collection M, if I add null matrix of order M by N to A, then it will look like this: Aij plus 0, that will again by the, since Aij is the element of F and 0 is the element of F, so this 0 is the additive identity. If I add 0 to Aij, I will get the element back. So it will give you the matrix A. By commutativity of addition in matrix, addition of matrix, I will get A plus 0 is equal to A is equal to 0 plus A. Therefore, 0 acts as an additive identity of M. If A equal to Aij belongs to M, then Aij belongs to F for all Ij. So minus of Aij belongs to F. Let minus A be the collection of all the negative minus Aij's. Okay, then minus A belongs to M. Okay, as Aij belongs to F, F is a fill, so additive inverse minus A also belongs to F. Yeah, minus A is the collections of the all element minus Aij. So minus A belongs to M. Then A plus minus A will be this. Mine here, I am writing directly here. Aij minus Aij. Do not write this directly, but you instead this you should write Aij square bracket. Then inside the square bracket Aij, then write plus. Then again take within bracket minus 1. Then write square bracket Aij, because in case of matrix, subtraction is not defined. We define subtraction in terms of addition. That is A plus minus AB can be written, A minus B we cannot write in matrix. We can write A plus minus 1 into A. Okay. So A minus Aij, that is A is an element of F, minus Aij is the additive inverse of Aij in F. So it will be additive identity 0, and this will give you the null matrix of order Mn, that is A plus Ia is equal to the null matrix, and by commutativity of the matrix addition I can write it minus A plus A. Therefore minus A acts as an additive inverse of A. Hence M plus is an additive abelian group. Now we are going to show M is closed under scalar multiplications. For that we will consider a scalar alpha belongs to F. Then since Aij belongs to F, okay, alpha Aij belongs to F. Okay, alpha is an element of F, Aij is an element of F, alpha Aij is again an element of F because F is closed under multiplication. Therefore, alpha of matrix A can be written as square bracket of alpha Aij which belongs to M. That is, M is closed under scalar multiplications. Finally, we take AB be two matrices of M. That is, AB and B are matrices of order M by N, and alpha beta be any two scalars in the field F. Then alpha a plus b is written in this way: alpha aij plus bij. By using left distributive law, we can write in this form. Then again, we can write this by using the definitions of matrix addition. Okay. Then finally, I will get this one. So first condition is satisfied. Second condition, I can similarly obtain. Third condition, alpha beta A can be written as alpha beta Aij. Then by associativity of the multiplication in F, as alpha beta belongs to F and Aij in belongs to F. So by associativity of the element of F, I will get alpha beta A. Next, if 1 is the unity element, then 1A can be written as 1 Aij. Since 1 is an element of F, Aij is an element of F. So 1 into A is equal to Aij is equal to Aij. That is from the additive inverse, not additive inverse, multiplicative inverse property of F. I will get Aij. So this will be the matrix here. Finally, we can show that this M, the set of all M by N matrices over, is a vector space over a field F. These are the questions for your practice. You can solve this question. So that complex field is a vector space over the real field R. Next is V is the set of all convergent real sequence. Then VR is a vector space. You also solve these two questions. In case of any problem, any difficulty, you can ask me. I am here to help you. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.